So the informal definition of a limit, I gave you the formal one was that epsilon delta one that we saw the other day, but we're going to stick with the informal definition of a limit. The notation is the limit as x approaches a, so this is the limit as the x values approach a specific x value, a, of f of x equals L. L is just a y value, so the limit is simply the y value that the function approaches as x gets closer to a. So oftentimes you can plug in a to the function and it will tell you the limit. We usually look at functions that are either have holes or asymptotes or jumps there, but if you have a nice continuous function, anywhere along that continuous function, the limit is whatever y value you get when you plug in an x. Okay, that's it. It's just a y value. So the notation literally means what you see up in blue here. The limit of f of x, there's the function, as x approaches a, that's this portion down here, equals L. There's L. And if you remember on our little geometer sketchpad thing, the L was in the middle of the little green band. And A, I think, was called C on the geometer sketchpad. It was in the middle of the little blue band. So if we can make f of x arbitrarily close to L by taking x to be sufficiently close to A, but not equal to A, then the limit exists, and it is L. So there are three ways to find a limit. One way is numerically. You just go ahead and kind of what you did remember when it said animate by 0.1 or animate by 0.01 or animate by 0.001? We had those three different options, right? So that's what you would do on your table is you would plug in values closer and closer and closer to A and look on your table and see what is it getting closer and closer and closer to in terms of a y value. Tedious and often inaccurate. You can have funny things happening with functions on even a very small interval. So I got to be careful about that. But numerically or using tables, okay, that's what this is using tables. Graphically, there it is. Works if f is easy to sketch. Our graphing calculators, the TI-84, will sometimes not give you the whole picture, so graphing can be a little bit dangerous. You might want to combine graphical with numerical, look at the tables and the graphs. But if the inputs, are such that it can handle them, then your graphing calculator would. Sometimes it's better to use something like some kind of software. It will show you better. I'll show you an example today of where your graphic calculator lies, but we can see it with computer software a little better. And then finally is analytically. And analytically means it could be as easy as substituting in the number to the function, if it's a continuous function on at that particular value, A. Sometimes we have to use things like factoring and canceling, or complex fractions, or trig substitutions to rewrite things. And so there's a lot of algebra that can be done to evaluate limits, and that's what we're going to focus on, is the algebra, or analytic methods using algebra. There's some methods in calculus that you'll be introduced to next year for evaluating limits as well. We're going to focus on the algebra ones. You may have seen this before. Somebody keep me in on this.
Contestants, find the limit of this equation.
Calling somebody else fat won't make you any skinnier. Calling someone stupid doesn't make you any smarter. And ruining Regina George's life definitely didn't make me any happier. All you can do in life is try to solve the problem in front of you.
The limit is -1.
Oh, crap. I lost.
That answer is incorrect. And we are in a sudden death. If Miss Heron can answer this problem correctly, we have a winner.
Limits. Why couldn't I remember anything about limits? Limits. That was the week Aaron got his haircut. Oh, God, he looks so cute. Okay, focus, Katie. What was on the board behind Aaron's head? If the limit never approaches anything, the limit does not exist.
The limit does not exist.
our new state champions, the North Shore Mathletes.
Found that clip. The three ways a limit fails to exist. You can have different one-sided limits. You may remember the two that look like this on Geometry Sketchpad? We had one down here, one up here. So from the left, it approaches a different value than from the right. Also, we had the one where you had the vertical asymptote. On the right, it was heading off towards infinity. On the left, down towards negative infinity. Okay, that's what we mean by that. Different one-sided limits, you would write does not exist. D and E is usually how we do it. Does not exist. Unbounded. Okay, the limit approaches infinity. So when you have a vertical asymptote there. And then the last one, probably haven't seen before. I'll show you an example of it in just a minute. The limit infinitely bounces between two values. So we have an oscillation. And so the limit fails to exist because it bounces between two values so quickly and so often that it does not exist. So three ways a limit fails to exist. Now if you could pull out your graphing calculators, we're going to see if we can graph each of these right here. So I'm going to open up mine. All right, so what you need to do here is we're going to type in absolute value of x over x and have it graph it so we get a picture of it. If you go to the math key, first column, fourth button down, hit math, go right arrow to num, and you'll see ABS, that's absolute value. On mine, it shows the absolute value signs. On yours, it may just say ABS if you have the classic mode. So we want absolute value of x, and then divided by x. And if you think about it, before I even graph it, what's happening here? If I plug in, for example, a positive 3 for x, absolute value of 3 would be 3 divided by 3 would be 1, right? What if I put in something like 5? Positive 5. I would still get 1, right? What if I put in a negative 5? Negative 5 on top will become positive 5 over negative 5, which will be negative 1. And if I put in a negative 3, I'd get a 3 over 3. It'd be 3 over negative 3 would be another negative 1. So do you see what's happening with this? It's either negative 1 or positive 1, right? And so this is an example of one in which the limit from the left of x equals 0 is negative 1, and the limit from the right of x equals 0 is positive 1. So the limit fails to exist, but only at one point. It only fails to exist at x equals 0. What gets confusing for students is we only focus on these problematic points. Anywhere else on this function, the limit exists. It's either negative 1 or 1, right? Like if I ask what's the limit at x as x approaches negative 3, it's negative 1. Or the limit as x approaches 2 up here is 1. Can't move it down. There it is. Anyways, my board's off again. So that's what the graph of that one looks like. So that's an example of the first way in which a limit fails to exist. So if you could draw a picture of that. Go ahead and draw a picture of that one for part A. And then let's move on to part B. Move on to part B. We're going to do 1 over x squared. So we go to y equals. And we clear this out. And we type in 1 divided by x to the second. And then we graph it. And see what happens here. So do you see which one that is? Maybe you can draw a quick sketch of that one for part B. Do that right now. It just keeps on heading up. It doesn't stop. From the left and from the right, they're both heading up to infinity. So they're both heading to the same place, but it's what we call unbounded. There's a vertical asymptote right there at x equals 0 or on the y-axis. So it just keeps on heading up. As a matter of fact, if you look at the table here, you can see it changes to scientific notation. Here's the table. I think it might have just frozen on me. Okay, there it goes. So you can see it switched to scientific notation. These are actually really small numbers, really close to 0, and these numbers in the second column are really big. You'll see 2.78 E6. That means 2.78 times 10 to the 6th. So it's heading up there really quickly as it gets closer to 0. Okay, the last one on there is the most interesting one, and I'll show you both on the calculator and on Desmos what it looks like. So we have, look at this last one, limit as x approaches 0 of sine of 1 over x. So make sure you're in radian mode. Check your mode, make sure you're in radian mode. Bam, right there. Then we're going to type in sine of 1 divided by x. Sine of 1 over x, and graph it, and it does some funny things here. Uh-oh. Actually, mine is frozen. So you should see it oscillates a whole bunch right around here. It's kind of normal through to here, and then just jumps all around. It actually disappears for a little while and then comes back. This is an example if your calculator is lying. It's not telling the whole truth. Okay, so on Desmos, I'm going to type in sine of 1 divided by x. And there it is. You see that? You know, it comes in, it's pretty normal, and then all of a sudden it just goes boom, 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 back and forth so fast that it just does not have a limit, and then mellows out and takes off again. But really close to 0, this isn't oscillating. It just oscillates too much to have a limit. So the limit fails to exist because of the oscillation happening right here. So if you could draw a sketch of that one, that'll work. So kind of comes in and then bounces back and forth. Then you could zoom in on this. It just almost looks like a solid piece because it's just going back and forth so fast. So there isn't any little small interval that would fit with our definition that we looked at on Geometry Sketchpad. You're just not gonna get that. In any small interval, you have a y value up here near 1, and then another one down near -1, and so it just never is approaching 1. You can see that in the table as well. Okay? So limit fails to exist in those 3 different cases. All right? Back to the notes here. All right. Left-hand limit. I don't know if you can see this here. I'm going to make it a little bit bigger. So now you can see it. You see that little minus sign there? And on the right-hand limit, make it a little bigger. You'll see a little plus sign. And so we can have one-sided limits that exist, whereas the limit at that point A does not exist. We've seen examples of that with our step function, or our little salt and pepper function that's either at 1 or -1. So as we slide from the left, f of x approaches L as x approaches A. This is the limit as x approaches A from the left. That little minus sign means we're only looking at the one-sided limit as you come in from the left. And then the plus sign down below here, we're only looking at the one-sided limit as x approaches A from the right. So I have some functions here in which we're going to determine the following one-sided limits. And you're welcome to do it on your calculator. On your worksheet, you can see the little plus or minus sign. So the first one is we're going to evaluate that function as it comes in from the left, and then the second one from the right. You get back to Desmos here. We'll do absolute value of 2x. So do absolute value of 2x divided by x, and we can answer both of those questions. Okay, very similar to the one I saw we had before, right? Except this one is either at -2 or at +2. So what's the limit as x approaches 0 from the left of that one? See it? Yeah, from the left it's -2, from the right it's +2. So go ahead and write that in. That's each of the first 2. You can see it pretty easily there. So limit as x approaches 0 from the left was -2, and from the right was +2. What about C? Let's go ahead and graph C. Do you know what it will look like? Clear this. We have x minus 1. And we're going to divide by, not multiply by. So x minus 1 divided by x squared minus 1. And x minus 1 over x squared minus 1. Right. So on this one, I'm asking for the limit as x approaches negative 1 from the left. So the limit as x approaches negative 1 from the left. So as I come into negative 1, I'm approaching from the left here. Where is this function headed? South. Right on down to negative infinity. And so you would just write that. Right, negative infinity. And it's not that negative infinity is, that's just where it's approaching. So we're going to write that in. This one heads towards negative infinity. And then the last one on here. Let's go ahead and graph that last one on here. It's square root of x plus 2 minus root 2 over x. Okay, so we have square root of x plus 2 minus root 2 divided by x. You can see the limit as x approaches negative 2 from the right. If you could, this is 1 right up here. Halfway in between is 1. So can you estimate about where it's going? Somewhere between, does it look like here would be 1 right here, so maybe somewhere around something just a little bit less than 1. It's actually 0.707 is what it's approaching. You can see that with the table. If you try to look at a table here, but it's approaching 0.707. If you do it on your graphic calculator and look at your table right here, negative 2, you'll see that it's really close to 0.707. Maybe I'll pull that up and show you. Right, so if you graph it and then go to second table, you can see my table, I'm starting right around 0. If you want to, you can go to second and then window, and it will give you a table start. A good place to start the table might be negative 2, because that's where I'm approaching. And then that next one, you know what the triangle means up here? Change, and yeah, so this is a very small change of about 0.0001. Okay, it's because it's in scientific notation. But if I go back to second graph and look at my table, do you see what it's approaching as it gets closer to negative 2? It's not showing all the decimals past this, but this is like negative 2.0001 and so forth. But from each side of this, it looks like I'm getting very close to 0.7. Do you see that? We're coming in on the right here and coming in on the left from down here. So our limit on this one is about 0.7. It's actually 0.707. And 0.707 is actually equivalent to root 2 over 2, I believe. Remember root 2 over 2 showed up a lot with our unit circle? All right. Okay, we're going to use the graph of G to find the limits here. Graph of G. So I need to, this will go quickly, so watch carefully as we go through this, and I'll have you try some of these pairs. Limit, we're just going to look at the picture. Limit as x approaches negative 7 from the left. So as I come in from the left here, where is this thing headed as x approaches negative 7 from the left? What are my y values approaching? Negative infinity. What about the limit as x approaches negative 7 from the right? It's going to positive infinity. So what is the limit then? What is the limit then as x approaches negative 7? Yeah, it does not exist. So the limit as x approaches negative 7, do you see that here? It doesn't exist because from one side it's headed to negative infinity, the other it's headed to positive infinity, so we'd write d and e. It does not exist. Okay? So limit on the left, limit on the right, going to different places, so the limit at that point does not exist. The limit as x approaches negative 3 from the left of g of x. So limit as x approaches negative 3 from the left of this function. Let's see, let's find negative 3. Here it is. So it's approaching from the left. We'll just keep coming in from the left here. What value is it approaching? Yes, it's approaching 1. What about from the right? Where is it approaching? Also 1. So what is the limit as x approaches negative 3? It is 1. The left and right hand limits, you see here and here, are the same, and so that is the value of the limit, even though there's a hole there. It was like the very first example we saw last week on Geometry Sketchpad. But what is the value of the function g of x at negative 3? That's what this is asking for. It's 4, yeah. So the value of the function, it's not a continuous function. The limit would have to equal the value of the function to be continuous. So we do have a hole here, right here. The limit exists. The limit is where the hole is. The function, though, is a different value. There's no way to approach this single dot from the left or from the right. So there's no limit of 4. It's a limit of 1. What about the limit as x approaches 3 from the right? So as x approaches 3 from the right, here we go. Where's that headed? That's going to infinity. And the limit as x approaches 3 from the left. It's negative 4. And what is g of 3? G of 3 is this dot right here. Negative 4. And what about the limit as x approaches 3 of g of x? We have negative 4 here, infinity here. Does not exist because the left and right hand limits are not equivalent.